Okay, we're gonna go ahead and do one more bonus example. This one's gonna be really cool because it's gonna have a bunch of variables in it. And our goal today for this example is to show that the inverse of this matrix, ABCD, the standard 2x2 matrix, is in fact what we said it is. We're gonna use this technique to show this is in fact what you get. That's a D. So we're going to use this technique and show this is in fact what you get. This looks a little scary. It just involves a little bit of algebra and fractions. But in fact, it works exactly the same way. We're just going to go ahead and apply row operations and alternate between scaling and zeroing out until we get the identity on the left and get something on the right. Let's just go ahead and get started. So to find the inverse matrix, we're going to start with the matrix on the left and the identity on the right. And the goal here, just to remind you, is what we're really doing is we're solving the equation AX equals the identity. And this X equals is hidden in this bar. So we're just applying row operations to the left and row operations to I. And if we can turn this into the identity, then what's literally translated back is X, which is the same, must be the same thing as A inverse, is what's ever going to be on the right. So what's the first step? Well, the first step is we need to take care of this pivot position. So I should mention, we're going to assume something here. This is not that big of an assumption, but it is important. We're going to assume that A is not equal to 0. So we're going to scale everything by A. So we're going to scale everything by 1 over A rather. And this is the same thing as before. The only difference is instead of a concrete number there, we have A. And now just like before, we have that 1 that we want, but now we have this C we need to zero out. So we're going to take row 2 and we're going to subtract out C times row 1. So keep in mind that whatever coefficient is here is exactly the number that's here. If you scale then zero out, scale then zero out, that's what's going to happen. So what happens now? Well, the top row doesn't change. The bottom row is going to become 0. Now this one becomes a little messy. This becomes D minus C times B over A. The next one becomes minus C over A. That's coming from C times the first row. And then finally 1 minus 0 times C. So we're almost halfway there. We have that 1 and we have that 0. We're going to spend this time first before we do anything is we're going to simplify this guy. And we're going to do this with a common denominator. So we're going to put an A over A here. That's what we're going to do. And then make it one fraction. So what happens when we do that? This becomes 0. And now this is, let's just go over this. We create a common fraction here so we can add the tops, rather subtract the tops, and divide by just A. And the rest of it remains the same. And now, just like before, we have to scale this guy. So we're going to take row 2, and we're going to scale it by A over AD minus BC. That's just the reciprocal of whatever number is there, and put that into row 2. All right, so we chose that specifically to be a 1. All right, now we might seem like we have a mess here, but we're going to take minus C over A times A over AD minus BC. Let's move this 0. And then we have 1 times A over AD minus BC. Let's take a minute to simplify this. So here those are A's are going to cancel, and this just is what it is. Stays that way. And we're almost there. We have those 2 1s where we want them. We have that 1 where we want it. And now the only thing left to do is to kind of solve for that and zero out that entry, the B over A. So to do that, we're going to take row 1. We're going to subtract B over A times row 2. Right, so we chose the B over A to be specifically to zero that one out. So that's going to be a 0. All right, now this is where things might get algebraically odd. We're going to take minus B over A. So, no, sorry. We're going to take what's currently there, and we're going to subtract B over A times minus C over AD minus BC. We're going to take 0 minus B over A times A over AD minus BC. And then the bottom we have the same thing. Nothing changed there. That's a D. All right, so let's simplify. So one of them is those A's are going to cancel. So the A's cancel, and on here we have minus B over AD minus BC. And now this other one is where things get a little strange. So what we're going to do here is we're going to multiply the top and bottom by AD minus BC on the top and the bottom, and that creates a common denominator. So here we have AD minus BC all right, and then adding across, we have a minus and a minus. That becomes a plus BC over A times AD minus BC. All right. And we're going to simplify this one more time. All right, and now you'll notice that this BC cancels with this one. And once you cancel that one, this A cancels with that. So what do we have all together? We have 1, 0, 0, 1. And on the right, we have D over AD minus BC, minus B over AD minus BC, minus C over AD minus BC, and A over AD minus BC. And if we factor out these guys, what's this matrix become? We can factor out that 1 over AD minus BC. We have D minus B minus C and A, just like we want. So this shows that you can actually use these row operations to compute exactly what the inverse of a 2 by 2 matrix is. Now you may be wondering, I made a slight assumption when we started. The one assumption we made was what if A is equal to 0? We made that assumption in the beginning. Well, if A is equal to 0, then the first step you have to do is you swap the 2 rows, and then you do all the row operations and you swap back. You can try it. You'll get the same thing. And then you might be asking, well, what if C is 0? Well, if C is 0, then we have that this pesky denominator, both A and C are 0, then this denominator is necessarily 0, and you're out of luck. So one of A or C has to not be 0 for this to work, for there to be an inverse. And so this gives you the generic formula for a 2x2 inverse. You can apply the same idea for a 3x3, but you're going to have 9 numbers and 9 variables floating about, and it doesn't come as nicely as this. All the entries are products of at least two entries, and this is in 6 terms instead of 2. So I wouldn't recommend it. In any case, have fun.